2, which is here. So we'll start by taking some questions from this, if anybody has any. John, okay, sure. So this asks us to use synthetic division. So the first thing I'm going to do is kind of draw my synthetic division setup. To figure out what number goes on the outside, I'm going to take that divisor, set it equal to 0, and then solve it. So 4 is what's going to go on the outside. And the numbers on the inside are going to be the coefficients from this polynomial. First, before I start writing those in, though, I'm going to check to make sure that all the degrees are covered. So I have an x to the 5th, 4th, 3rd, 2nd, 1st, and then constant. So I don't have any missing parts. So I don't need to add any extra zeros in there. So I'll bring the first number down, and then 3 times 4 is 12. I add down that 0. 0 times 4 is 0. I add down that's -7. 4 times -7 is -28. I add down that 6. 4 times 6 is 24. I add down that's -5. And 4 times -5 is -20. I add down that's 1. So that completes the division. All I have to do is kind of process my answer. So the first number on the right is my remainder, and my constant term, my x coefficient, my x squared coefficient, my x to the 3rd coefficient, my x to the 4th coefficient. So I'd say my answer here is 3x to the 4th. I could write 0x to the 3rd, but I don't really need to write it because it's a 0, so I'm just going to skip it. Minus 7x squared plus 6x minus 5 plus my remainder over my divisor. And that's the way I'd write my final answer then. Is that okay, John? Okay. I thought I saw some other hands too as John was raising his. Eric? Number 5. Okay. So to do these problems on 5 through 10 or whatever is there, I'm going to kind of be using the factoring diagram that I talked about in the video. So if I look at the notes that I would have taken about this is kind of the factoring diagram that I made. I put my notes in there into the OneNote here today. So if you didn't see that yet, I don't know that you would have because I just did it a little while ago. But this is the factoring diagram that we've talked about in the video. So as I'm doing this, I'm going to kind of refer to this and the steps included in here. Okay. So first thing I'd check for is the greatest common factor. Well, clearly there's not one, right? Next thing we look at number of terms. We have 2 terms. If I go to the 2-term branch, the first thing I look for is a difference of 2 squares. Clearly that's not, because the exponent is odd. You need an even exponent to even have a possibility of that. The next thing I look for is a sum or difference of 2 cubes. So I see that exponent on the variable is 3, so maybe I can rewrite this as a sum of 2 cubes. So x cubed, well, that's just x to the 3rd. And 27 is 3 to the 3rd, right? 3 times 3 is 9, times 3 again is 27. So I can say that my a value is x and my b value is 3. So when I use my sum of 2 cubes factoring pattern, which I'll write down here for us so you can see what I'm filling in, I'm basically going to fill in the a and b values to this right-hand side. So a plus b is going to be x plus 3. A squared is x squared. A times b is 3x. And b squared is 3 squared, or 9. And then I should check to see if I can factor either one of these pieces. Now, the x plus 3 is linear, so that clearly isn't going to factor anymore. And that x squared minus 3x plus 9 that quadratic piece that's coming from the sum or difference of two cubes is never going to be factorable. So you could try to factor, but you will be unsuccessful. So that's as good as we can do. Is that okay, Eric? What else do we have? Maddie? Nope. Mackenzie?
Yeah. For number 3 on the 2, would you have to write out all the zeros for x to the 9?
Yeah.
Okay.
Yeah. Do you want to do it?
No.
Oh, okay. So yeah, there'd be a bunch of them, right? What, like 6 of them or 7 of them or something? No, 8 of them. Because the 9th has 10 terms. We only got 2 of them down there. So you'd have the 1, 8 zeros, and then the negative 1. It'd be a lot of synthetic divisioning to do. I think you should get remainder 0, though. Anyways, others. Happy to do more if you have more. If not, that's okay. Okie majokies. All right, well, the plan here today is we're going to do a few more factoring examples for polynomial factoring. And then we're going to talk about solving polynomials by factoring. And we'll see, that'll probably be enough for today. I don't think I want to move past that point yet, because the next ideas is a lengthy one that I'd like to start fresh at the beginning of a class rather than just like cram in 15 minutes or whatever's left at the end. Doesn't seem to make a lot of sense to me. So I'm just going to do a couple more examples using this factoring diagram that I outlined in the previous lesson. So I know I was gone for that part too, is also part of why we're just doing some more examples now, to just see some more stuff in real time where you can follow along and ask questions, and maybe it's a little easier than watching my video. So the typical directions for something like this would just say like factor completely. And we'll do some examples of this. So let's say we did 4x to the 5th minus 16x to the 3rd minus 180x. So again, if we're looking at that factoring diagram, the first thing we look for is a greatest common factor. Is there a greatest common factor in this problem? Yes, right? What is it? Look a little closer, check the variables too. 4x, right? Everybody's good with that? So I take the 4x out. I'm left with x to the 4th minus 4x squared minus 45. Once I've done that, I'm basically going to ignore that greatest common factor out front for the rest of this problem. Now, it's going to come with me all the way to the answer, but I'm not going to use it again to do anything when I do any of this additional factoring. So I'm just going to focus on the x to the 4th minus 4x squared minus 45 part. Everybody's okay with that plan? Okay, so the next thing I would look at is the number of terms. How many terms do I have on that piece? 3 terms, right? Everybody agree? I have the x to the 4th, the minus 4x squared, and the minus 45. 3 terms. If I look down the 3-term branch, the first thing it asks is it in the quadratic form? What do I mean by being in the quadratic form? Well, the biggest exponent on my variable should be twice the smaller exponent on my variable, and then I should have a constant at the end, which is exactly what we have in this case, right? It isn't exactly quadratic, but it looks like it's quadratic. Okay, since it's in the quadratic form, the next question is the leading coefficient 1? Is that going on in this case? Sure is, right? The coefficient on the x to the fourth is 1. So I can use my shortcut factoring. So just like for a quadratic, I just need two things that multiply to give me negative 45 and add to give me negative 4. What are those two numbers? Negative 9 and positive 5. Very good. Now, if I was doing x squared minus 4x minus 45, I would write x minus 9, x plus 5 from that, right? Here, though, we have x to the fourth minus 4x squared minus 45. Basically, the only difference comes, instead of writing x minus 9 and x plus 5, we're going to write x squared minus 9 and x squared plus 5. So whatever the variable is on that middle term tells you the variable in your factors, basically. Is that okay there? Again, fairly easy to realize why that has to be the case if you think about it. Can be kind of easy to forget to do if you're going super fast, so just be a little mindful of that. Everybody so far so good? So that completes the 3-term branch. Now I need to check each one of these factors to see if we can do anything more. So x squared minus 9, I need to go down the 2-term branch. So the first thing I check in the 2-term branch is it a 2 squares? Definitely is, right? And that's like a first semester question. We could just factor that to x minus 3, x plus 3. No need to make any more work than that. We should check to make sure those factors we can't do anything more with. They're both linear, so we know we're done, right? You guys know what I mean when I say linear? Their degree is 1. Okay. Now we have to go back up to the x squared plus 5. Also a 2 terms problem, so I go down the 2-term branch. Is that a difference of 2 squares? No, right? For a couple of reasons. One, it's an addition problem. 2, 5 isn't a perfect square. Either one of those reasonings are fine. To say it's not. So going down the 2-term branch, the next thing we check, is it a sum or difference of 2 cubes? Again, definitely not, right? The exponent on the variable isn't divisible by 3, so it can't be a sum or difference of 2 cubes, right? The exponent on the variable is 2. 3 doesn't divide that, so it can't be a perfect cube in any way. In addition, 5 isn't a perfect cube, right? So this thing is just done. So our final answer, we're going to have the 4x from out front, the x minus 3x plus 3 from that piece, and then the x squared plus 5 from the end that we couldn't do anything else with. Does that feel okay? We're going to do a couple more just to kind of get used to this process and using this factoring tree. But again, the sub-skills are not so difficult, right? It's basically just doing a problem from chapter 4, but there's like a lot of iterations of the factoring you have to do. But most of the factoring steps are not so bad, right? It's just making sure you're doing them kind of in the right order and doing the right thing at the right time. Let's do another example, though. So 2x to the 7th plus 6x to the 5th plus 16x to the 4th minus 48x squared is what we'll start with. Again, the first step is always look for that greatest common factor. Is there a greatest common factor in this case? Look carefully at the variables. 2x squared, right? They all have at least 2 x's on them, so we can take out a 2x squared. Oops. And here I made a typo when I wrote this down. There was some dust on my calculator. This symbol is supposed to be a subtraction symbol. My apologies there. Okay. Next thing we look at is the number of terms. How many terms do we have here? What do you guys think? 4, right? Because again, all we're worried about is the part inside the parentheses. 4 terms there. We have 4 things that are being added or subtracted. If we look at down the 4-term branch, the first thing we need to check, can we do factor by grouping on it? So let's check that, or the first thing we should try maybe. So to do this, I'm going to do 2 terms together, and then I write a plus sign, and then everything else goes into the second group. Just as an FYI, you can actually really just want the groups to be equal sizes. Whether they have 2 terms each, or 3 terms each, or 4 terms each, you can do grouping more than just with like 2 groups of 2. You could have 2 groups of 3, or you could have 3 groups of 2, depending on how much stuff you have. More often than case, in our situation, it'll just be like 2 groups of 2. But it's a more versatile technique than just that. Anyways, continue on. Now what we do is we look for a greatest common factor in each group. For x to the 5th plus 3x cubed, what's the greatest common factor? X cubed, very good. So we'll take that out. And in the second group, negative 8x squared minus 24, what's the greatest common factor? I would do negative 8. Since both of them are negative. Typically, you want the leading coefficient in each group to be positive. So even if that was negative 8x squared plus 24, I would still take the a negative 8 out. Okay. Now to check to see if it can actually be factored by grouping, those 2 pieces have to be identical, which they are, right? We have x squared plus 3 in each of them. So we can continue factoring this by grouping. So we still have that 2x squared out front. Squared out. That leaves us with x cubed minus 8. So far, so good. Again, if I'm going too fast or if I do something you don't understand, speak up. We can slow down. We can rediscuss something, go over something in more detail, clarify a point that maybe I skated past that you're not sure about. Again, I know I was gone when we did this initial lecture on this, so this is part of the reason why we're taking some more time today to do some more examples to make sure that we're just kind of all on the same page and we have a decent understanding of what's going on here. Because again, it's not like the most complicated thing in the world, but it helps to see some examples in real time that you can interact with a little bit. Okay, continuing on, now we need to check to see if x squared plus 3 or x cubed plus 3, or I'm sorry, x cubed minus 8 can factor more. In each case, there are 2 terms. So on x squared plus 3, the first thing we check for is a difference of 2 squares. It's definitely not one of those. Why is it not one of those? Because the 3 isn't a perfect square is perfectly good reason. You could also have said, or because it's an addition problem instead of a subtraction problem. That would be fine too. Next thing we do is we look for the sum or difference of two cubes. Definitely not one of those either. How do we know that? The exponent is even rather than a multiple of 3. Yep. That's fine. So this is done. We couldn't do anything better than that. Now let's, again, that's the two-term branch. The first thing we do is look for a difference of two squares. Definitely not one of those, right? Why not? The exponent is odd, or the 8 isn't a perfect square. Either explanation is valid. Both are reasons why it wouldn't. Next thing we do is look for, that one looks promising though, right? Because we have something cubed minus a constant. So we'll try to write this as something cubed minus something cubed. Well, x cubed is just x to the third. 8 is 2 to the third. So this is a difference of two cubes. Sorry, two cubes. Where the a is x and the b is 2. So using the difference of two cubes formula that I'll write down again right here for us so you can see what we're getting into, I'm just going to substitute the a and b into that side of the pattern. So a minus b becomes a squared becomes x squared. ab becomes 2x. And b squared becomes 2 squared. Any questions on how I made that substitution or how I did that factoring there for that piece? It is worth noting that we should check the results of that to see if we can factor any of those pieces anymore. Can we factor x minus 2 anymore? No, right? It's linear. Can we factor x squared plus 2x plus 4 anymore? No, that's the quadratic part that comes out of it, sum or difference of two cubes. Those parts will never be factorable. You could try, but there's not two things that multiply to give you 4 and add to give you 2. Not real numbers anyways. I mean, there are two numbers, but they're imaginary. So, for our final answer then, we have the 2x squared. We have the x squared plus 3. And just as we're working on these, I want to point out too that I'm including like all these little steps that I'm showing and like questions that I'm asking myself. You don't need to include that stuff when you do this work. Like, it's fine. Just show like the intermediate steps, like if you can do anything. It's perfectly fine. I'm doing this because these are notes. And we weren't, I wasn't here the last lecture. You guys did that by video. So I'm just trying to connect these ideas back to the video you watched last time to make the notes a little bit more clear if you go back and look at these and then go look at the factoring tree. But you don't need to include that work, right? So for like this problem, if you had wrote down like, you did this, you showed this step, you showed some of that work to get down to here, and then you just showed how that piece factored to that piece. Like, that's enough in terms of work shown. Like, you don't have to show like all these little step-a-rooskies unless it helps you, in which case you're more than welcome to do that, right? Like, I'll never tell you not to do showing more work than is helpful, right? That's always fine. I'm just talking about like that you don't need to do that if it's like, boy, this seems like a lot of work for something that could be much shorter. And it is, right? I'm just trying to be thorough. You know what I mean? Okay. Let's do one more example, and then we'll move on about solving and then combine those two ideas together. So the next one is this one. So again, first thing would be to start with looking for a greatest common factor. Is there one? No way. Okay, so the next thing we do is we look at the number of terms I have here. 3. So if we go down the 3-term branch, we have to check to see if it's in the quadratic form. Is this in the quadratic form? So again, what you're checking, you need to check to make sure oops, what just happened there? That the biggest exponent is the next exponent, and the last piece is constant. So yes, we are in the quadratic form. It basically just needs to look like a quadratic, right? It's not actually quadratic yet. And since then we check the leading coefficient to see if that's 1, which it clearly is. So it tells us we can do the shortcut factoring. So just like if it was a quadratic, we're just going to find two things that multiply to give us negative 27 and add to give us positive 26. Those two things would be 27 and negative 1. Very good. So that's going to give me x cubed minus 27 and plus 27 and x cubed minus 1. Everybody's okay why it's x cubed? Okay. If you're not, speak up, but I'm going to maybe start writing down a little less on the factoring steps here. Is that okay with you guys? I'll just kind of say what I'm doing aloud, but not necessarily write it down. Now that we kind of have a little feel for the factoring tree, that you guys are okay with that, right? Or you can say no if you want me to keep writing. I'll keep writing. You just don't care. You'll do whatever I say. Stand on your head. Okay. Good. Nobody stood on their head. All right. So now we have to check each one of these factors to see if we can do more. They're each 2 terms, so that we start by looking for a difference of 2 squares. X cubed plus 27, is that a difference of 2 squares? No way. There's like nothing difference of 2 squares about it, right? Next thing we look, is it a sum or difference of 2 cubes? Certainly looks like it would be, right? X cubed is x to the 3rd. 27 is 3 to the 3rd, so it definitely fits the pattern. So the sum of 2 cubes factoring pattern is this. So when we put this together, we have x plus 3, x. And then if I look at the x cubed minus 1, we have to check the same things. Is it a difference of 2 squares? Is it a sum or difference of 2 cubes? Certainly looks like it, right? X cubed can be written as x to the 3rd. 1 can be written as 1 to the 3rd. So the difference of 2 cubes factoring is this. So that gives us x minus 1 times x squared plus x plus 1. Oops. Are we okay with what I did there? Now I should check each one of these 4 things to see if I can factor them anymore. X plus 3. Can I do anything with that? Nope, it's linear. X squared minus 3x plus 9. Can I do anything with that? Nope, it came from the sum or difference of 2 cubes. How about the x minus 1? Nope, it's linear. How about the x squared plus x plus 1? Nope, it came from the sum or difference of two cubes. So this is as good as we can do. Feel okay there? Relatively speaking anyways. Okay. So let's talk about solving then. Oops, I picked a different color. Okay, so if we're going to try to solve by factoring, the key idea from first semester that we're going to use is this thing called the zero product property. Zero product property stated that if you had two things that multiply to give you 0, one of those, or at least one of those two things, must have been 0. So the way we use this is it allowed us to solve things like x squared plus 9x plus 18 equal to 0. We could factor into some plus 6x plus 3. And then since that product is equal to 0, I can set each factor equal to 0 and then solve each one of them independently. Everybody kind of remember doing that from last semester? You should have gotten a lot of practice doing that. That was our first quadratic solving method that we would have talked about. A pretty useful one is that in that it's pretty easy to use. So what we're going to do now is we're going to apply this same set of ideas to solving polynomials. We're going to use those three polynomials that we just factored in our examples as solving problems, so I don't have to refactor anything in the interest of time. We can just worry about, like, okay, once we factored it, like, what do we do then? Is everybody okay with that? So I'm going to do my examples just up here on the side, like next to what I did before. Like, whoop. So if I want to solve by factoring, the problem set is going to look slightly different in so much it's equals 0. Notice this is the exact same polynomial that we factored in our factoring example A. It's just now equal to 0, so it's a solving problem instead of just a regular old factoring problem. The first step would be to factor this thing. But we already did that, so I'm just going to steal the work from over here. Is everybody okay with that? Just as a means of practicing the solving part without having to redo all the factoring again. I wanted to treat these like two discrete skills, so I wanted to do all the factoring examples before I did the solving so that we didn't get confused on the two skills, as one is part of the other necessarily, but okay. And then we can apply our zero product property, so I can just take each of the factors and set each one equal to. Keep in mind that if the polynomial didn't equal 0 at the beginning and you factored it, you can't do anything with that. Has to equal 0 in the beginning. If it doesn't equal 0, just make it equal 0. Move everything, add or subtract everything onto one side and then get after it. You know what I mean? All right, so 4x is equal to 0. Just divide both sides by 4. X equals 0. Add 3 to both sides. We get x equals 3. Subtract 3 from both sides, we get x equals -3. Those are all easy to do. X squared plus 5 is quadratic. Last semester we learned the 3 ways to solve a quadratic would be by factoring, solving directly, or using the quadratic formula. If you're solving a polynomial, the quadratic that you get at the end will never be factorable, because if you could factor it more, you would have factored it when you factored the polynomial. So you're always going to be either using direct methods or the quadratic formula. Remember, the quadratic formula works in every case. The direct solving directly works only when you have just x squareds and no x's, like we do in this case. I prefer to use solving directly if I can, because I think it's a little bit less cumbersome than the quadratic formula, although it wouldn't be bad in this case. I'm still going to just solve directly, so I'm just going to subtract 5 from both sides. Then square root both sides. Since I'm square rooting both sides, it creates a plus or minus. Since I'm square rooting a negative, I get an I. And then the square root of 5, I can't do anything else to simplify because it's a prime number, so I am done there. So those would be my solutions. Do we feel okay on that? Again, none of those little individual questions were very difficult. Basically what happens is you take this polynomial, you factor all the way down, and it just turns into a bunch of problems that you would have done in semester 1, right? A bunch of pretty easy problems. The worst case scenario is maybe you have to bust out the quadratic formula, but you know, it's not the end of the world. Okay, let's do the next one as an example. So I'm going to zoom back out so I can see the problem. So I have this. The first step then would be to factor it. Since we already factored this in the previous problem, I'm just going to kind of steal and put it over here. Again, if you're doing this problem fresh, you'd likely have to factor that part by hand yourself. It would be unlikely you would have done the exact same problem somewhere earlier that you factored that you could have just stolen it, stolen the work from. But again, the point of this is just to practice the solving part right now without having to deal with the factoring piece. Since this is all the way factored, everything is being multiplied together, those factors, and set them each equal to 0 and solve each one of them separately. So the first piece I can just divide both, square root both sides. Note that I don't need to worry about the plus or minus here because the square root of 0 is 0. And positive 0 and negative 0 is just 0, right? So when we get a little bit further in, that actually is a special situation that would just happen there, and we'll take note of it. But for right now, I'm just going to let that pass by. Here, just like we had x squared plus 5, I'm going to solve this directly to get plus or minus I root 3. And we can add 2 to both sides. And then lastly, we have a quadratic that contains both x's and x squareds. Here we're going to be forced to use the quadratic formula, right? We can't solve this directly. We know it's never going to be factorable, or else we would have factored it when we factored the polynomial. Four, 2 squared is 4, minus 4 times 4 is 16, 4 minus 16 is 9. So the negative is going to create an I, right? 12 is the same thing as 4 times 3. So the square root of 12 is the square root of 4 times the square root of 3. And the square root of 4 can just be 2. So I'm going to write this as 2I root 3 all over 2. And then to reduce this options with a common denominator of 2. So negative 2 over 2 is just negative 1. Here the 2 in the numerator and denominator reduce. So my best answer would be negative 1 plus or minus I root 3. If you're taking a standardized test, that would be the solution that would be in the multiple choice. Oops. Make that a little bigger for everybody. How's this feeling so far? The solving is probably no big deal, right? Just using techniques that we would have used last semester. You might have to do like a couple of last semester problems inside of one here, but it's still not really any more difficult than solving a quadratic was, right? You just might have multiple quadratics that you have to deal with, but that's not the end of the world. Feeling okay? I have one more that I'd like to look at, and then we'll finish up and let you guys start on the homeworks. We have quite a bit of time left here that you can get a good jump on things. Nobody's going to be mad about that, right? All right. The last one that we did an example on. So again, we factor that. I'm stealing all my work for factoring from the previous example. Using the zero product property, I can set each factor equal to 0, and then I can solve them. Second one, I have to use the quadratic formula. Negative of a negative 3 is positive. Negative 3 squared minus 4 times 1. Everybody's okay that I shortcutted through some of showing the work on the quadratic formula there? Okay. So the square root of 20, or negative 27, the negative creates an I, right? 27 is 9 times 3. So the square root of 27 can be the square root of 9 times the square root of 3. And the square root of 9 is just 3. So I call that 3I root 3 all over 2. And I can't reduce that anymore, so that's good. Subtract 1 from both sides over there. Another quadratic squared minus 4 times 1 is negative 3. And the square root of negative 3 just creates an I. What do you guys think? It's all right? Okay. Homework 3. I'm just going to show you before I'll go back.